I see you there. You're not hiding. So hi and welcome. Hey, thanks for joining us here in my shop, Shadow and me. Yes, Shadow's in the shop today, not outside. So today what I'm going to be doing in this radio, I think the first thing I want to do is try to figure out why a couple of resistors are running really hot up here. These are big high wattage resistors, and yet they're getting very, very hot. So I think we're going to look into that. I think the way I'm going to do it is first I'm going to identify what they are, where they are on the schematic diagram, and try to figure out what kind of current should be in them and all that kind of stuff. And once we sort of have a grip on the situation they're in, we'll figure out why they're too hot. And a really good guess is one of these adjacent capacitors not doing its job. That's a good guess. Right, Shadow? So that's what we're going to be doing, and I'm pretty sure we're going to be visited by Shadow during most of this. Okay, so what I'm going to do is make a diagram as best I can on where these resistors are connected. So we'll start with this one, and I'll bet you one end is going to a grounded terminal. So there's a terminal here with quite a bit of stuff hooked up to it. Capacitor, resistor, resistor, all that stuff. No, just these. Just this, and this, not these two. Hooked up to this big terminal with a wire on it. Shadow, how can I make notes when you're sitting on my note page? Come on now. So one lead goes up. Can't even see what I wrote there. It goes up to a ground terminal. So grounded to the chassis. Pretty good so far. Okay, so that's about the best I can get. This photograph we're looking at is coming from Radio Museum. I'm a member of Radio Museum. If you're not and you're doing this kind of stuff, come on, become a member of Radio Museum. Okay, now, yeah, my radio is turned on a different angle from the photograph, but that's the best I can do there. So I had looked at this a little bit, but let's look at it together. Can I swing my mouse over that thing? Yes, I can. Great. Okay, excellent. Start at the top here. You can see this first capacitor in the photo, and I think these are all original parts. That looks like paper, and here it is here as a plastic molded. So you just come over a little bit further. Here is a burned resistor, and that radio looks like a very similar burned resistor in the photograph. Come over further, this blue capacitor is a bumblebee capacitor in the radio there. Bumblebee capacitors are not reliable. We come a little bit further, and you can see this one is also a bumblebee down there, right here. So I think I've just answered a question I had. Why did he, the last guy, for instance, leave this big paper capacitor here? You can see it in the photograph there. Because it was not a bumblebee. He went after the bumblebee capacitors and replaced them all. Probably a good move. So, for instance, there's a paper one here. I can see it in the photograph. There's a paper one here. This is not paper. It looks like this is something different. I don't know what that is. Looks like a bumblebee in the, I got beeswax all over my fingers, I think. So anyway, that's good. Let's look at these resistors. Go back to the resistors. So we'll start with this one. It appears to look almost identical to this in terms of its burning and that. The next resistor over is this one. In the photograph, it's white. It appears to have all of its paint. Whoops! Oh my gosh, what did I just do? I did something dumb here. Okay, I think I know what I did. There we are. Yeah, so try not to click an accidental mouse click. You never know what can happen. So there it is there. White in this radio, but black in this one. And the next one over is this resistor in that radio. You know, I don't know if that's burned or... I think it is. I think it's burned in that radio. Right in the middle it's black. Almost certain. You can see body and dot here. Red looks like silver on the end here, and then the dot is orange. So there's another hot, or once was hot resistor. You can see it in the photograph. It's quite nice in the photograph, but cooked up here. You can see the paper in the photograph, and actually a bunch of them in there. 1, 2. Oh, this must be the replacement for one of those paper ones. Still doesn't explain this long hanging wire here. This just isn't the way things are done. Okay, so we've kind of got an advantage with this photograph here showing us stuff. It's easy to make mistakes galore in this kind of situation. So I best not rush into anything here. I'm also under instructions to do the least I can do to the radio to preserve as much as possible of what it is as it stands right now. That doesn't mean I can't replace all this stuff. It just means there's no willy-nilliness going on here. There's got to be a reason behind everything I do. And there usually is. I like that approach anyway. I don't like the shotgun of the capacitors deal. Okay, so the picture isn't really revealing an awful lot that's going to help here, and raising a couple of interesting questions, especially where's this connection really supposed to be here? It'll be a tough one to sort out, but we'll get to that at some point. I think for now I'm going to go back to what I was saying before. I'm just going to replace these three. We'll take them out. We can test these, see what we got, put in new ones, because I'm pretty sure I can identify these on the schematic and get the correct size. And okay, that's what I'm going to do. First I got to go play with my cat for a while. That's right, I'm coming. Okay, it's taking a little bit of time. Keep my cats happy. And so I made this diagram. What I did was I drew initially the 3 capacitors just out here on the page. There they are, the 3 I wanted to find out. And then I just started adding components that I could trace off the end of them. Kind of, if I could figure out the value of it, I wrote the value down, and I looked on the schematic and tried to find something that matched this kind of stuff. And I managed to figure it all out. So I know which capacitor each one of these is. And I think we're going to take a minute, look at the schematic now, and consider each one of these and ask ourselves the question, could a short on the original capacitor burn up the resistors that are burned up? Or another even better question, really, about the current situation. Hey, that's a pun. The current situation with this, where these 2 resistors are currently overheating, we should really ask ourselves questions about that. Those 2 resistors, this one anyway, is this one, R13. And this one, you know, is not involved with this capacitor or these. This guy's connected here, but this resistor is no longer hot. Okay, so theory would be, yeah, I don't know. So let's do them one at a time. So pop this guy out. No, I'm going to change them all. Okay, it's getting a little later in the afternoon now because I've been away for a bit, but I'm back. I've changed the 3 capacitors in here. We're almost ready to test this, but first, why not test the old capacitors? So over here on my capacitor checker, we're getting ready to go. There's the 3 capacitors right there. A bit of a closer look. Okay, I'll stand here and cast a little shadow onto my checker. So which one first? Let's get the short leads here. So this is the first capacitor. This one doesn't look directly related to either of the two overheated resistors. But let's see. The molded shell is cracked right open here. There's a piece missing. Look at that. It's just coming apart, eh? That's typical of this kind of capacitor. Okay, 50 volts, regular style capacitor. This should close and pop open pretty quick. Okay, it opened all the way. Let's try 150 volts this time. So that's showing you that he's not 100%, but this is not a killer capacitor by any means. It's leaking enough that we really can't measure its capacitance accurately. So here we go to the next one. A Duranite. This one was a manufacturer unknown. Duranite. It's got that durable word in there. Yeah, are you? Really? Let's see. How durable are you? 50 volts. Even though it says 25 here, in case you can read it, it's actually 50 when you operate it. Here we go. Okay, popped open. 150. Well, 250. We'll give it a big whack there. 250 still opening. So this capacitor actually was good. So that's just a whole string of actually not bad capacitors I've been replacing here. Now this guy, it's a smaller one. It's a 0.05 gain. This is the one that was most likely to be burning up resistors if it was shorted. If it was shorted, the set wouldn't work at all anyway, so we know that's really not the case already. 50 volts, what do you do? Looking good. 150. This is a 200 volt capacitor, so that's not opening all the way. So not perfect. In fact, the blue one actually came out not bad. The other two, good to replace. No way to know until you take them out and do this kind of test. And not so wise to assume all old capacitors are bad actors. But I don't think we will have done anything here to solve these hot resistors. What we're going to find out in just a moment. Let me get my viewer going here. Top number is 35, so I'm just going to change the top of the color scale for, let's say, 45. Bottom, how did the bottom get down to 10? I must have been doing something goofy with this thing. 20 would be good at the bottom. So the color range is from 45 to 20, but the machine always works 100% regardless of how you control the screen display. I think we're ready. We're not going to hear this to start with. I'm just going to ignore the hearing part. We're just going to check the temperature on here. And by the way, I did a B+ test. Came out a little above 300, the maximum rating on these tubes. If I remember right here. That's with the two 45s sitting on my bench over there and not plugged in. You put those 45s in there and get them working, and probably the B+ will come down a little bit on there. I think we're ready. Just make sure everything's kind of safe here, safe enough. Here we go. Switch on. Okay, so I made some significant changes, so of course I'm using the dim lights. 103 volts, that's lots of voltage. Anybody getting hot yet? That guy's warming up. That guy's warming up. Okay, so they're already warming up. Not this one though. This one slightly. Now these got up to the point where they were bubbling their paint. It's really very surprising to me. Well, that's at 36. I really misunderstood what's going on down here with these two resistors. So maybe we'll look at that next. Why don't we do that next? Because it looks like there's two resistors in series going from the positive output of the transformer, or I shouldn't say that, going from here to ground, kind of wasting a bunch of power. I don't really understand what this is here for. Let me able to sort this out a little better. Okay, where are we getting to now? Okay, now we're getting up there. So that's at 50. That's 44. It's nowhere near as hot as they were. You have a little trouble believing changing those capacitors has caused any significant improvement with respect to, you know, current flows causing resistors to overheat. That's a bit far-fetched, I think. 45 now. No, I'm sorry, not 45. 57. Now it's getting up there. 48. Still going. 59. Still going up. So, you know, I guess we got to pick some temperatures here. The temperatures I have in my mind is 60 is as high as you want to go in the back of a radio. 90 is the point where components are really starting to degrade. 120 is a call the fire engines at 120. That's kind of how I view it. I got those numbers from working in the power industry, and they're related to how hot a cable can be operated. You may not realize this or not, but well, you probably do realize this. The whole issue with electricity is temperature. And if you can keep the temperature down, you can jam more electricity down stuff. It's really not very complicated. So although a lot of equipment comes with ratings of current, that's because electrical people have clamp-on ammeters and ammeters. Most electrical people aren't carting this kind of thing around or any other kind of thermometer. If they were, they would be using them. They would be using them to check the temperature of things, because it's the temperature that's critical, not so much the current flowing through it. So that's the story there. So with a device like this, wow, you jump way ahead in the world of electricity. So that's now 66, and this one's 53. And you know, this is with restricted voltage. There's only 100 volts on the machine. I put 120 on here. That's going to go up another 10 degrees. It's still too hot. The question we have is it supposed to be that hot, or is that okay hot from the radio's point of view? And not jumping in there to change these big resistors either, because look at how big they are. So if I can get around the problem here one way or another, I'd be happy. I'd rather not replace those great big resistors. I think they're just fine. I don't really know though for sure. What about this one over here? So this guy's also gotten up now. He's at 55. This red one. You can just see the top of it there. And is there anything else? Have I missed anything else in here? That's the tube socket base down there. Wow. Okay, so there's another one back in here. But, you know, that's not very hot. That one is around 35. That's just back in here. 60 out in the open, 40 all tucked in tight. 40 tucked in tight might be a bigger concern than 60 out in the open. So it's tucked in there, but so I think one of these little resistors is a little bit warm. And you know, I guess on a theoretical level, every resistor is a little bit warm. Okay, let's deal with this down here, and then I'm going to call it a day. Now, what is the deal down there? Let's take a closer look at it. I really don't know. This is a bit of the rewired, bit of the radio where the radio's been rewired. So let's see what we got here. Well, this looks very much like a ground terminal down here. Yeah. Metal pin, Jim? Come on. Don't be holding on to that. I don't know if this terminal is used on the cable that exists now. The other end, the other resistor is hooked up to, you know, what I would say is a positive terminal. Maybe I'm a little confused here. Maybe. It's always just possible. Confusion has entered the picture. So I'm going to read the voltage on these guys here. There, you can read it too. Okay, to the top of the capacitor there. Ooh, hot diggity dog. Minus 21. Let's try it. I did that, right? I got this grounded. Minus 21. So this must be that resistor trick that I was muttering about a video or two ago, where you can incorporate a resistor in the power supply in such a way that you sort of elevate. It's like the cathode biasing thing, only you're doing it with the entire radio. The entire radio is biased up, say, maybe 21 volts. And then if you need 21 negative volts, just go down and get them. And what the heck is all that doing here? So let me switch back to the close-up here. Well, what all's hooked up to this resistor anyway? Wrong button. So there's a black wire here. There's another black wire right here. Basically across these. So is this a ground terminal? Make a quick check here. Doesn't seem to be. So this is not a ground terminal. So it may be involved in the remade cable the guy made up, and it's going over the amp, and it's something to do with the amp. So maybe that's the B plus line. No, it can't be. It's got negative voltage on it. Where is the high voltage in here? It's this white wire here, coming from the capacitor. So even though this is a remade circuitry here, schematic might help a bit with this. And what's this yellow wire doing? Well, the yellow wire, it's just picking off a terminal over there, and then it's just going right to that, soldered to the top of this. This is the fake field coil. I'm pretty sure of it now. I was thinking more about how they bolted this in, so they used the same bolts as the guy up on top. That would never be done in a factory environment. Each device would have its own set of holes and screws. Well, for sure, this is the installed field coil. I didn't look at that photograph. Let me look at that. Ooh, if I got that photograph handy, can I get that in front of me almost instantly? Yes, I can. So in the photograph, son of a gun, there is something there. Son of a gun, that is sitting right there. That is there. Ah. Well, that blows my theory all out to lunch. Okay, so I'll have to back up the story just a little bit to say I don't. So this is what it's supposed to be, I guess. And where's the field coil? We're back to that. And my theory about bolting them on, sharing them, theory gone, theory destroyed. My credibility is destroyed. You know, my credibility can't be destroyed because I start without any credibility. Now, well, I'm going to turn this off before I make a big mistake. Stick my fingers in there. So what all is going on here? So there's two similar wires coming out here. You know what? Actually, it's these two are similar, and this looks like the center tap for them. Center tap. Center tap, minus 21 volts. That's a, these are biasing resistors on the center tap of the part of the transformer that feeds the plates on the 45s are every tube in here. Okay, so that's helpful. So this, where? So that would make this the center tap, and they'd be using part of the filter there to bypass the cathode resistors. How much resistoring did he put in there? Can't remember if I measured this. So typical cathode resistors are some hundreds of volts, hundreds of ohms rather. I don't like to go much beyond that. Okay, there could be a big voltage here still. Testing rate on the capacitor. Nothing. Okay, how much resistance? 680. So that's what that is. Now either he couldn't get the 680 with one resistor just like me, or he decided just like me to utilize two resistors to spread out the heat. Unfortunately, what's happening is this one resistor is taking all the it's taking it. And you know what? Let me get the close-up camera here, because when you look closely at that brown resistor, that's not a shadow. Where's the focus here? Let me get up close here with the focus. That is a shadow. Yeah, okay, that is a shadow. Okay. But so this resistor is the one that's taking the heat, though. Where's the value? I'm trying to spot the value on either one of these. So they're installed, so the values are hidden away. So I can clip these out. I know what the total value is. I'm just going to clip these guys out here. Clip them out. So cathode resistor with cathode current for the 45s. There would be a pretty substantial cathode current. I don't know if a 5-watt resistor would be anywhere near enough there. I don't know. Because that's what I got. I got 5-watt resistors. Hanging on there. Okay. 135 ohms and 500 ohms. So this is why this guy's taking all the heat. This is not 50-50 by any means. 500. So 500 and 135 combined is 635. It's roughly what I measured. So these things aren't damaged. Let's take a look in the manual for what the cathode resistor should be for two 45s and push-pull. Two 45s. I don't say an awful lot here. Class A operation. I like that. So they don't give it in push-pull. So, okay, in this kind of arrangement, plate supply 275 max. Cathode bias resistor. So under this kind of operation, it would expect with 180 volts on the plate, 1000 cathode, 250 volts, 1500 cathode. And I'm half that. That's for a single tube. I believe if you put two tubes in push-pull, you have one resistor serving two cathodes. You need half as much resistor to get the same voltage. So if this is suggesting 1500 and in the radio is about 750, that's really right on the money, or, you know, in terms of the book here. There's no error with that. Oh, you know what I didn't look at? Duh. And so I need to know what the plate current is on a 45. A 45 with a lot of pressure. So that'd be up. So maximum plate current, no, I'm sorry. Typical plate current, 31, 34, 36 at 275. 36 milliamps at 275 volts on the plate. So, you know, go a little higher and be a little off, maybe 40 milliamps flowing through each of the two tubes. That's 80 milliamps. At 80 milliamps. Oh, yeah. And so 80 milliamps squared. Right. Yeah, I'm not going to do this in my head. I'm going to do it somewhere else. So 80 milliamps, I'll do it in my head. 80 milliamps is roughly 100 milliamps is roughly 0.1 amps. 0.1 squared is 0.01, isn't it? 0.01 times 20 volts. So 0.01 times 20 volts, 0.2 watts. There's no watts. So this didn't work. I didn't get this right. So, I mean, how does this thing get hot with 0.2 watts? It doesn't. So I did something stupid. What's the square of 0.1? 0.1 times 0.1. 0.1 of 0.1, isn't it 0.01? 0.01 times 20. So factor of 10, 0.01 becomes 0.1 times 2, 0.2. 0.2 watts. Right. Oh, okay, I got something really wrong here when I think about it now. Just think, Jim. The 45s are out. The output transformer that would serve the B plus back to the 45s is not hooked up. The cathode resistor for the 45s, it should have zero current in it. It had zero heat in it, but it was hot. So I got something wrong here, definitely I have figured this out wrong. It's amazing how you can make all the puzzle pieces fit until one doesn't. So, well, let's just continue some wire tracing here. So the resistor is hooked up here, and to those two spots are these two black wires, which are a little hard to see, I'm sure, in the camera, especially if I put my head in front of it. One of those wires comes all the way up to here, and the other one's stopping here. So they're coming to two very similar. I think there's a terminal strip here and a terminal strip there. Resistors hooked around. I don't know how thinking like that is going to get me anywhere, but wow, you really got to look closely in here to see what they've done. So, what are they? I'm going to look at the schematic. I can't look down here. This is not the schematic, but up here it should be. Unfortunately, these wires, they just come into networks of resistors. So unless it's a weird resistor number, I'm going to have a hard time spotting it. How am I ever going to figure that out now? Because there's a connection going to a tube socket that I can trace. Ay, ay, ay. Okay, I'm not going to do this on camera. I got to sort this out. Okay, so you see I have the schematic up on the screen now, so we can kind of look things over here. So I've done a couple of approaches at trying to figure this out, and none of them have worked. In other words, I think I know what I found, and when I trace further, it doesn't add up anymore. So what I am thinking now is this transformer has a number of windings, only two of which have center taps. This is definitely a center tap lead, I'm sure, associated with these two wires. The other center tap is this, which is solidly grounded there. So if we look at the schematic, we find the winding with the solid grounding, and it's down here. It's the filament winding for the two 45 tubes, solidly grounded. So the other one must be the high voltage winding. It has to be this. This center tap in this radio comes over to a large capacitor that is attached back to the chassis. This is the amplifier. This is the wires going to the amplifier. You could even ask yourself, well, where are the filter capacitors here for this radio? These two? I don't think so. Not on this. They. So yeah, I turn on the camera too soon. I'm not ready to talk yet. That's really strange. So normally you'd be filtering. Off of this. Well, maybe these aren't. See, 35 and 37. 35 and 37. 35 and 37. 35, 16. 16 millifarad. So yeah, so 35 and 37, 36. These are all filter capacitors. 3 of them. Is there any more big ones in here? So I'm looking for a big number on this list. A big number. There's a couple. So these are probably in the amplifier, I'm going to guess. There's another one there. 25 microfarad. I'm pretty sure this is the amplifier capacitors. Well, that's my guess, really. Let's face it, I'm just guessing at that. But what else could they be? So here we are. So these 3, 35, 36, and 37. Well, find them. Find them somewhere. Somebody find them. 35, 36, and 37. So here they are in here. Now, one of the positive leads of one of these capacitors is hooked up to the center tap of this. It's got to be this one. Oh, it could be this one. The other side is, they're solidly grounded. Well, no, maybe not. So I don't see any negative terminals. Okay, bear with me, I'm just going to make a quick reading here with an ohm meter just to make sure the metal cans are actually connected to the chassis. Yes, they are. So that's basically the metal cans are the negative terminals of these capacitors, of which there are, in fact, just wait 1 second now. One of those terminals is painted black on that one. Okay, hold on, I'm flipping cameras. Oh, you were looking at a camera. You see, this is what happens in my shop. You have that view, but I'm looking over here at my computer screen, which you can't really see. It's just all the schematic there. So sometimes I forget what it is you're looking at, because I'm busy looking at what I'm looking at. So, yay. Okay, so this big capacitor here is a 2-terminal capacitor. 243 microfarad, 450 volt, black common negative. So this is it's a common negative. Doesn't necessarily mean it's at ground potential though. And it isn't. When I measure it, it's not. It wasn't. With those resistors there, it wasn't. Well, there you go. See, I thought I'd turn on the camera and just 1, 2, 3 explain this. I'm going to turn the camera off now. Okay, after lots of monkey business, making diagrams here, trying to chase all these wires around and redraw it and make sense of it, it suddenly struck me. That's the field coil. That's the field coil the guy put in. Now, older power supplies like to use coils in the power supply because they're very effective. Newer radios don't want to use coils in the power supply because they're very heavy and expensive. So eventually radios stopped using coils as part of the filter system in the power supply, replaced them with just a resistor, and then heavied up the filter capacitors a lot. Like in here there's 16 microfarad with choke coils, or field coil if you like in there. Field coil is just a choke coil of a sort. So that's what this is, because I noticed when I was looking at the schematic, the field coil resistance is around 800 ohms. Voila, that's the best he could do out of his junk box. So, this is effective if you've upped the size of the 16 microfarad capacitors, and of course he has. He's got 2 big ones in here. These guys are all 40-50 microfarads. 4 of them here all together as called for. So that's the story. This is not the field coil he stuck in. No, that's an original part. And I did manage to trace this and really match it up against the schematic, as difficult as that was. So when I measured the field coil voltage drop and I said 21 negative, it's just because of the way I had the meter on there. I could have turned it around and gone 21 positive volts. So now, can this be responsible for the hum? No, because this wasn't involved in the humming amplifier. Could this be introducing another hum? This is why I'm working on the receiver at this point, because for all I know, the receiver has its own hum. It's going to fire over to the amplifier. And with any luck, maybe the two of them are going to buck each other. and they'll go away. So I'm left here now with a decision what to do about this. You know, I just stick one in, or I can put an 800 ohm one in there to match the resistance of the field coil a little better. Got to think about it. Okay, well, we're making progress here, bit by bit. Yeah, a bit of progress, bit by bit. So thanks a lot for watching today. So I'm going to think a little more about this, and then tomorrow we'll continue on these hot resistors here a little bit. And maybe we'll actually play the radio and see what it sounds like. We can take some more voltage tests. There's a voltage table in this. You know what? There's a voltage table in here. So we can do that tomorrow. We can look through the voltage table, make some measurements, see if they're matching up. And but so far, as much as I'm struggling with what the fellow did to this radio, I haven't found anything egregious that he did. He must have really known what he was doing. Doing this 20 years ago in a shop, much more challenging than me now because of the information I have available. I don't really know what information this guy had. Maybe he had it all. I don't know. Okay, thanks a lot for watching. I'm just babbling at this point. And I'm on my way to enjoy my day doing other things. See ya.